In this video, we continue our theme of exploring ways to draw organic structures, which is a fundamental skill for a variety of concepts related to organic chemistry, biochemistry, and other fields. We'll be applying these types of techniques throughout the rest of the course. Taking a look at this video, the theme is going to be drawing condensed structural formulas. This follows up from our earlier video. That was video number 305, where we looked at drawing Lewis structures. In Lewis structures, we showed details about all of the lone pair electrons, all of the covalent bonds, every single atom, and every single formal charge. In condensed structural formulas, as the name sort of implies, we are going to implicitly, rather than explicitly, show some of the information. In the case of condensed structural formulas, we will show all of the atoms but all of the lone pair electrons are implied, meaning that by virtue of the fact that you don't see formal charges listed on the atoms, you can infer how many lone pair electrons must be present in order to fill the octets on all of the atoms and give no formal charge. In addition to the lone pairs being implied, we also omit most of the bonds. So in other words, for example, rather than showing this CH3 group here at the right-hand end of this example molecule with a carbon with lines going to 3 different hydrogens representing those covalent bonds, instead, it's implied, since the 3 hydrogens, H3, are listed immediately adjacent to that carbon, that all 3 of them have to be bonded to that carbon in order to fill the octet on that particular carbon. So based on this condensed structural formula example here that we see, we are able to infer features of the molecule such as where all of the covalent bonds must be, where all of the lone pairs must be. So condensed structural formulas are going to show us all of the atoms, but they're going to omit or imply that lone pairs are there based on the fact that we don't see formal charges on individual atoms, and most of the bonds are going to be omitted. So in this chain here, you'll notice that all of the covalent bonds are omitted. It doesn't mean that they're not actually there in the physical molecule that would exist in real life, but instead, the way that we've drawn this is going to allow us to infer who's connected to whom as we go through this chain. Now, we do see a few of the covalent bonds shown, like we show the double covalent bond here leading between the carbon and oxygen, because that comes branching off of this core chain that is running through the molecule. We need that there to emphasize that there is a double bond there rather than a single bond, because it's implied as we come through here in the core of the molecule going left and right that all of these bonds would be single bonds unless otherwise shown. So the double bond here we had to show explicitly, both because it is a double bond and that has to be shown explicitly to indicate that it exists, and also because it's branching off of the molecule going a different direction than the rest of the structure. So we have to show that as a line or lines coming off to indicate the covalent bonds there. So let's go ahead and take a closer look at what the rules are for drawing condensed structural formulas and how we would convert a Lewis structure into a condensed structural formula. We'll dive into some example problems to illustrate the topic of how we convert Lewis structures to condensed structural formulas. And you should be able to convert in either direction. If you were given a condensed structural formula, you should be able to show what the Lewis structure would be that corresponds to that. Or likewise, if you're shown a Lewis structure, you should be able to draw the condensed structural formula that would be equivalent to. Let's illustrate by doing an example here where I'm going to draw out the Lewis structure for a particular molecule. Remember, Lewis structure shows all the atoms, all of the bonds, all of the lone pair electrons, and all of the formal charges. So it shows as much detail as one could possibly show about a particular molecule. The downside to Lewis structures is that they take, as you're seeing here, a pretty long time to draw. They're quite cumbersome. So especially as we get more deeply into the fields of organic chemistry and biochemistry, it's not always convenient to spend the time to draw out all of these structures in this level of detail. Sometimes it is more efficient and preferable thus to draw in a more condensed way, hence the condensed structural formula. So this is our Lewis structure here on the left, showing all of the bonds, all of the lone pair electrons, and if there were any formal charges, we would have to show those as well. There aren't. Now, we are tasked with asking ourselves the question of what is the condensed structural formula going to look like here. So we'll work through this problem together to understand how we would go about doing this. In our condensed structural formula, what we will do to convert from our Lewis structure to our condensed structural formula is when we see groups like this CH3 group here, if all three of those hydrogens are connected to the same carbon, we can represent that by showing it as CH3 or alternatively as H3C. Those are going to be equivalent ways of going about showing this. CH2 groups, the carbon that's directly bonded to two hydrogens, we could represent as CH2 or equivalently H2C. And then when we have something like this at the end where we have a OH group, we could abbreviate that just as OH, omitting that line that would connect the oxygen and the hydrogen atom. So we fill this into the condensed structural formula. So I'm going to begin at the far left end of the molecule here. So we had a CH3 group. We refer to that as a methyl group, by the way, if you're naming it. So we have a CH3 group there, and I've abbreviated it as CH3. Having that hydrogen directly adjacent to the carbon indicates that those two groups are bonded, and having that subscript 3 there means there's not just one hydrogen bonded to that carbon, but there's three of them, and that's a very common theme we'll see amongst organic molecules. Then next in the chain we have CH2, so we fill that as CH and then subscript 2, since there's two hydrogens directly bonded to that carbon, and since the hydrogen is listed there adjacent to it, that indicates or implies that the two hydrogens are there. And then continuing on down the chain, we have two additional CH2 groups. So I fill that as CH2, CH2. That completes coming through the structure here. That takes care of this carbon, and this carbon, since all three of those, here, here, and here, are all three CH2 groups. And then finally, this carbon that is furthest to the right in the structure and corresponds to the carbon over here, that carbon is directly bonded to OH. So therefore, I fill in at the end here OH. I don't put the lone pair electrons onto that oxygen because the condensed structural formula omits lone pair electrons. So condensed structural formula, omit your lone pairs. It's implied that those are there. So you would have to envision that for this to have a formal charge of 0, that it would have two sets of lone pair electrons, but those are implied that they are there. They are not something that we show explicitly in a condensed structural formula. In the interest of time, it's implied. And condensed structural formulas omit most covalent bonds, except in the case of branches that come off of the chain going up or down, and double or triple bonds. We would have to show those as lines like we did in our Lewis structures. That was not the case here because we don't have any double or triple bonds to deal with, and we don't have any branches because all of the atoms other than hydrogen all are found in this linear fashion here, where we can sketch out from one end of the molecule to the other without having to branch off of that and backtrack. So all four of our carbon atoms are here, 1, 2, 3, 4, and then our OH group right here. And we can backtrack who's connected to whom here. One thing that people get confused about is when we look at this region of the molecule, for example, we have CH3 and CH2. How do we know which hydrogens are connected to which carbon? We have to infer what is the case there by recognizing that all of the carbon atoms need a total of 4 bonds, and that there's generally only going to be one way to do that. So the carbon out here at the left in order for it to have a complete octet, it has to have possession of those 3 hydrogens. In other words, those 3 hydrogens all have to be bonded to this carbon, otherwise that carbon wouldn't have a complete octet. Then likewise, we can infer, since this carbon, we see the H2 next to it, those 2 hydrogens have to be bonded to this carbon in order for it to have a complete octet, and that carbon would also have to be bonded to the carbon at the left and the carbon at the right to finish off its octet. And we can go all the way down the chain, making those same sorts of inferences to recognize that the structure we see here would correspond to this Lewis structure. Now, one way that we can condense things down even further is that if we have multiple identical groups that are all in a row here, such as the CH2 groups, we can actually break that down even further by putting a parenthesis, CH2, and then another parenthesis and a subscript 3 to indicate that there are 3 CH2 groups, CH21, CH22, and CH23. And then we could plug that into the condensed structural formula by attaching our CH3 group out here to the left, and then our OH group on the right-hand terminal there. So this would imply that the CH3 group is bonded to the string of CH2, 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 and there's only one way to arrange that where it fills the octet, and that would be to have the 3 CH2 groups in a row there like so, and then the last one of those CH2 groups is connected to the OH group so that everyone has a complete octet. As perhaps you're gathering from the number of times I've mentioned it, the octet rule is king here, and that's the guiding principle as you are drawing out condensed structural formulas and linking them back to Lewis structures, is we're drawing them in a way that makes it clear how we fill the octet for each of the atoms, even though we're not showing all of the covalent bond lines and we're not showing any lone pairs. It's implied that these all have to have a complete octet, and we're showing a representation that would allow us to see how the octet rule would be filled for all of these, even though we're not showing lone pairs and we're not showing most of the covalent bonds. Let's dig into another example problem where we are asked to convert the condensed structural formula that we see below into a Lewis structure. Now, to get started on the right foot for that, we need to remember that a Lewis structure is going to be one that shows us all of the bonds, all of the atoms, all of the formal charges, and looking at our condensed structural formula here, condensed structural formulas would have to show the formal charges on atoms as well. Since we don't see any formal charges here, that means there's none in the Lewis structure either. And additionally, Lewis structures will show us all of the lone pair electrons, which we will have to determine where the lone pairs are at in this particular molecule. So drawing this as a Lewis structure here, what I'm going to do is begin by dissecting how we're going to fill the octet for each of the atoms here. I like to start at one end of the molecule, left-hand end or right-hand end here. And I'm going to start from the left since most of us read left to right, but you could definitely start from the right-hand end if you're feeling a little confused about what's going on at the left end of the molecule. Usually better to get some early wins and build your confidence than start somewhere in the molecule where you don't have a clue what to do. So starting at the left-hand end, we have a CH3 group. And that CH3, the abbreviation CH3 means that those 3 hydrogens are directly bonded to that carbon atom. So I plug that in like so. So we have our carbon there and the 3 hydrogens that carbon is bonded to. That's our carbon right here. And the 3 hydrogens it's linked to are here, here, and here. And then to fill the complete octet for this carbon, we currently have 3 covalent bonds. It needs a 4th, and it gets that 4th by the carbon that is to its right there. So I'm going to fill that in to my Lewis structure here, showing a line to connect the next carbon in the chain because we have to show all of the bonds explicitly. That particular carbon is directly connected to 2 hydrogen atoms because it's a CH2 listed there. So I'm going to fill in those 2 hydrogens here and here. I'm filling those in up and down just to keep the line going through the molecule left and right like it was up top to help keep myself organized, but you aren't required to put the hydrogen up and down. You could have spaced it out however you want here with the 4 atoms, with a hydrogen going off to the right and a hydrogen going up, or a hydrogen going down and then the next carbon coming up, or however you like to do it. You just have to fill in the ends of those lines with the 4 atoms that are directly bonded there. So we have our carbon atom in pink, and I'll highlight that in pink down here as well for emphasis. That's connected to 2 hydrogens here and here. And then those 2 carbons were linked together like this by a covalent bond, so that's what we would see right here. And then carrying on down the line, draw a line to the next atom, keeping in mind that this carbon always has to have a complete octet. It's a safe bet to fill in those 4 lines equally spaced, showing that the electrons repel. And the next position that it has to be bonded to is this carbon right here. So I'm going to highlight that carbon in yellow along with the H2, which are the 2 hydrogens that it is connected to. I'll fill that in here as CH2, so CH and H. And I am also going to go ahead and highlight that in my structure here to remind myself that those are the atoms that correspond to the CH2 group in our condensed structural formula up top. Now, this carbon currently has 3 covalent bonds, so where do we get the 4th? We get the 4th by going on down the chain and making that inference that it has to be connected to the carbon atom right here. So I'll go ahead and fill that in, highlighting in gray here that CH group. And I'm going to go ahead and fill that in here. So we have our carbon directly bonded to a hydrogen, filling in my 4 bonds there to that carbon. Any one of those 4 bonds could be the bond to the hydrogen atom. It doesn't have to be up, down, left, or right. It doesn't matter. They're all going to give a structure that is equally good. So I'm going to put it just down here in this lower spot right here. So that corresponds to our hydrogen atom that was connected to the carbon in gray up top in our condensed structural formula. So condensed structural formula right here, coming down to here was our CH group. That carbon, in addition to being bonded to the hydrogen, is bonded to the carbon in yellow, as we see here in our Lewis structure. And then it has a line going to an OH group. So we need to show that here as well. We have a line going to O, and that oxygen is bonded to a hydrogen, so I'll go ahead and fill in that hydrogen like that. And then coming from here, we have our CH, which we showed in gray, and that carbon, to fill its final spot here, its final octet in the template, we need it to be plugged onto the carbon of the CH3 group that's here at the right. So I will go ahead and fill that in as a carbon. And that carbon is directly bonded to 3 hydrogens. So we have hydrogen, hydrogen, and hydrogen here. And I'll go ahead and highlight that for completeness here. Go ahead and get my green highlighter and do CH3 highlighted up there in green, CH3 down here in green. And to fill the octet on that carbon, we infer that it has to be connected to the carbon that was in gray up here. Now this is our Lewis structure in terms of showing definitely all the bonds are taken care of, all the atoms are taken care of, all of the formal charges are taken care of, because if there's no formal charges listed in the condensed structural formula, that means there can be no formal charges down here either. Formal charges have to be shown in all types of structural drawings. There's no way around that. And then lone pair electrons are what we haven't filled in here. And there are 2 ways that we could do that. One way that we could do that is we could go back to the video where we learned about drawing Lewis structures and we practiced filling in lone pair electrons according to the total number of valence electrons that we would calculate for this structure, and determining by calculation how many lone pair electrons we have to work with and filling those in here, since this is the only atom that's missing an octet. Or we can go back to our information on formal charges and realize that in order for an oxygen of no formal charge, it absolutely has to have 2 sets of lone pair electrons and 2 covalent bonds, and recognizing that this is the only way, the only electron arrangement possible that will allow us to create an oxygen with no formal charge, we can assume that that is the correct way to fill it in. So this is the only electron arrangement that gives oxygen with a 0 formal charge. And that's definitely an oxygen that has a 0 formal charge because of the fact that it has no formal charge shown on the atom here. We can imply that. So we now have successfully converted a condensed structural formula into a Lewis structure in this problem.